Good day to everyone. My name is Nathaniel Kaya, the leader of the Group 8, and today we'll explore the complex topic of micro operations. This is a basic idea in computer design that helps make modern processor make better and faster. So in computing, we often see instructions as the basic units of work, but behind every high-level instruction, there are many smaller tasks that the CPU needs to do to make the instruction work. These smaller tasks are called micro operation or micro ops for short. So here are three objectives that throughout our presentation. So the first one is we will discuss the basic classification of arithmetic's micro micro operations. Second is to identify the interconnection of four full adder circuits to provide a four binary adder. Lastly, describe the block diagram of a four-bit combinational circuit. So that's all. On to the next important.
Hello everyone, I am John Nicholas P. Taan, here to report a few things about arithmetic microoperations. Generally, arithmetic microoperations deals with the operations performed on numeric data stored within the registers. Its basics are classified into the following: addition, subtraction, increment, decrement, and shift. Some are classified as add with carry, subtract with borrow, and transfer, load, etc.
Hello everyone, my name is Joed Vargas. Today I will explain what is arithmetic microoperation. The operation implemented on the data stored in registered are known as the microoperation. The various microoperation including addition, subtraction, increment, and decrement. Example of adding microoperation: the statement instructs the information of registered R1 to be inserted to data of registered R2, and the sum must be converted to the registered R3. On subtraction microoperation, subtract microoperation are using minus operator. 1s complement add 1 to the registered which obtains subtracted. Example, 1s complement adding on R3 minus R1 must be converted to registered R3. On increment and decrement microoperation, in increment and decrement microoperation, it usually implemented by adding and subtracting 1 to the from the registered respectively. Example of this is 1s complement adding R1 equals R1, and on decrement 1s complement subtracting R1 equals R1. That's all. Thank you.
I'll give you a quick overview of arithmetic microoperation. Let's start with some basic operation from the table. R3 gets R1 plus R2 means we add the contents of R1 and R2 and store the result in R3. R3 gets R1 minus R2 means we subtract R2 from R1 and store that in R3. Now for the complements, R2 gets R2 prime means we flip the bits of R2 which is the 1's complement. R2 gets R2 prime plus 1 gives us the 2's complement which negates the value of R2. R3 gets R1 plus R2 prime plus 1 means we add R1 to the 2's complement of R2 which performs subtraction. We can also increment of decrement values. R1 gets R1 plus 1, increments R1 by, and R1 gets R1 minus 1, decrease R1 by 1. Now when we need to add 4-bit numbers, we use 4 full adders to create a 4-bit binary adder. Finally, there's the 4-bit the incrementer, which is a circuit that adds 1 to 4-bit number. That's the basic arithmetic microoperation.
The add microoperation requires registers that can hold the data and the digital components that can perform the arithmetic addition. A binary adder is a digital circuit that performs the arithmetic sum of two binary numbers provided with any length. A binary adder is constructed using full adder circuits connected in series, with the output carry from one full adder connected to the input carry of the next full adder. The following block diagram shows the interconnections of four full adder circuits to provide a 4-bit binary adder. With add microoperation, it needs registers to store data and its digital components to perform addition. And as it states here, binary adder is a digital circuit that is designed to add two binary numbers regardless of their length. Meanwhile, full adders can add two binary digits plus a carry from a previous digit, producing a sum and a carry out. When you connect multiple full adders in series, each one handles a bit of the numbers being added. The carry out from each full adder becomes the carry in for the next one in the series.
Hi, my name is Virginia and I will be discussing the binary adder diagram. A binary adder is a digital circuit that performs the arithmetic sum of two binary numbers. A binary adder is constructed using the full adder circuits connected in a series, with the output carry from one full adder connected to the input carry of the next full adder. In a 4-bit binary diagram, you can see a series of full adder circuits from input carry, which is the C0, to output carry, which is the C4. Sa isang full adder, merong two binary numbers na tinatawag, which is the augment bits, yung A, and then the added bits, yung B. So, yung A0 plus B0 equals to S0, or the sum 0. Then carry 1. So, yung carry from the previous full adder will connected to the next full adder, which is the B1 and the A1. Take note that the augment bits, which is the A, and the addend bits, which is B, are designated by subscript numbers from right to left, with the subscript 0 denoting the low order bit. And also, the carry input starts from C0 to C3 connected in a chain through the full adders. C4 is the resultant output carry generated by the last full adder circuit.
Using half adders, HA, here's a breakdown of the diagram. Half adder HA, each box labeled HA is half adder. A half adder adds two single bit binary numbers and outputs two values, S sum bit and C carry bit. A3, A2, A1, A0 that represents the 4-bit binary number that is being incremented. The rightmost bit A0 is being incremented by 1, the least significant bit. Connections. Each half adder has two inputs, X and Y. For the first half adder, rightmost, one input is the least significant bit A0 and the other is the binary 1. Being added, the carry output C of each half adder is fed into the next half adder as an input along with the corresponding bit from the original number A1, A2, etc. S0, S1, S2, and S3 represents the output some bit after the binary increment, and C4 is the carry out from the most significant bit. Is an explanation. The process begins at the rightmost half adder where A0 is incremented by B1 by 1. The sum bit S0 is the result of this addition while the carry bit is passed to the next half adder for A1. The same process continues for A1, A2, and A3 where each bit is added to the carry from the previous stage, producing some bits S1, S2, S3, and passing the carry to the next stage. The carry out C4 represents whether there's an overflow from the most significant bit. This is a 4-bit binary number is incremented by 1.
Hello, my name is Carl Dexter Tortor, and I am about to give you a brief summary on what this topic is about. First of all, we need to explain what binary is. Binary is a number system that only uses 2 digits, which are zeros and ones. It is also the fundamental language of computers. That's why learning how binary works is significant in understanding how computers operate. Meanwhile, a binary adder is a computer part where 2 binary numbers are added together. The way it works is first, you need to have a box like where it can hold and store the data, called the register, and a component that can perform arithmetic operations or an ALU. In this case, addition. Then we add a pair of bits, one at a time. Then it passes any carry to the next pair of bits. Lastly, it produces a final answer that's the sum of the 2 binary numbers. For example, here we will use 13 or 1101 in binary as the augend and 5 or 0101 in binary as the addend. Each time we add a number that the sum exceeds 1 or is equal to 2, we carry a number until we see another number that exceeds 1 or is equal to 2. We release that number or until we reach the left side of the equation. Here we see the total is 18 or 10100 in binary. That's all, thank you.
Hello, my name is Christian Paul Sutenedero, and I will explain the combination of arithmetic microoperation in a binary adder subtractor. Arithmetic microoperation like addition and subtraction can be combined into a single circuit using full adders and exclusive OR, XOR gates. By connecting XOR gates to the input of the full adder, a control signal M can determine whether to add or subtract. When M is equals to 0, the circuit performs addition, and when M equals to 1, it performs subtraction by inverting one of the inputs.
The binary adder subtractor, an important digital circuit in computing. The binary adder subtractor is a circuit that can perform both addition and subtraction of binary numbers using a single design. It utilizes a control signal to switch between addition and subtraction modes. When the control signal indicates the addition, the circuit processes the inputs normally. Moreover, when the signal indicates the subtraction, the circuit inverts the bits of the second operand and adds one to it. These methods allow the adder subtractor to efficiently handle both operations. In summary, the binary adder subtractor is a versatile circuit that combines the functionalities of addition and subtraction, making it essential in digital systems.
Okay, let's now talk about the binary adder subtractor. With the same circuit of a binary adder, we can modify it to make the same circuit also perform the subtraction micro operation. By taking the other input's complement or its inverse, we can manipulate the circuit into performing the subtraction micro-operation using the full adders that we already have. Subsequently, we can leave this input as it is to make the addition micro-operation on our full adders. In this diagram, we can see that this is achieved by introducing a mode line M along with the B input, both passing through an XOR gate. The result is then combined with the A input as inputs to the full adders. When M is at low logic, the circuit acts as an adder, and when the mode input is at high logic, the circuit will act as an subtractor. By toggling M between 0 and 1, we can control the operation mode of the 4-bit binary adder subtractor circuit. And onto the binary incrementer.
Hello, my name is John Lloyd Gibbs. Let's break down how a binary incrementer circuit works. First, when we want to increment a binary number, we start by applying a logic 1 to one of the inputs of the least significant half adder. The other input is connected to the least significant bit to the number that we're incrementing. As the number gets processed, the carry output from half adder is passed to the next higher half adder, so that the circuit can handle binary addition properly. In this system, the circuit receives 4 bits named A0 to A3. It adds 1 to this input and gives us the new incremented number as the output, labeled S0 to S3. The last important thing to note is the carry output C4. This will be 1 when the numbers being incremented is 1, 1, 1, 1, which is the maximum value for 4 bits. Thank you.
Hello, my name is Chris John Vasco, and welcome to this explanation of a 4-bit binary incrementer. Imagine you have a 4-bit binary number. This device, known as an incrementer, adds 1 to that number. Here's how it works. Each bit of a binary number is processed through a half adder, which adds the current bit and any carry from the previous operation. We start by adding 1 to the least significant bit and also a 0. If this results in a sum that generates a carry, that carry is passed to the next higher bit. The same process happens to all of bits, moving from the least to the significant to the most significant. If a carry is produced at the final bit at 3, it results in a carry out, indicating that the number has overflowed beyond its 4-bit capacity. The final result is a new 4-bit number where each bit has been correctly incremented according to the carry produced by the addition. To sum it up, a binary incrementer simply adds 1 to the binary number bit by bit, passing any carry to the next higher bit. Thank you for listening.
Hi, my name is Joker Togle. I'm talking about a binary incrementer. A binary incrementer is a device or algorithm designed to increase a binary number by 1. In the context of digital logic and computer system, it's a fundamental operation used in various tasks such as counting, memory addressing, and looping. Here's my opinion. Binary incrementers are extremely efficient since incrementing a binary number by 1 is one of the simplest operation in digital circuits. The process often involves flipping bits and propagating the carry, which can be done quickly using combinational logic. Most hardware implementation of processor include dedicated circuitry for fast binary incrementing, making it near instantaneous operation.
Hi, I'm Lynette Verastige. I'll discuss about the increment micro operation. which is a simple but essential operation in digital circuits. It involves adding 1 to the value stored in a register. So here's how a 4-bit binary incrementer circuit works. First, input. The circuit receives the 4 bits of the binary number to be incremented. Second is least significant bit. Input, which is a logic 1, is applied to one of the inputs of the least significant half adder. This effectively adds 1 to the LSB of the binary number. So third is carry propagation. The carry out from each half adder is connected to the carry in of the next higher order half adder. This allows the increment operation to propagate through all the bits of the binary numbers. Fourth is the output. The incremented value is generated and stored in the output registers. So fifth, the last one is carry out. The output carry will be 1 only after incrementing the binary number. This indicates that the incremented value has overflowed and is now a 5-bit number. In summary, the increment microoperation adds 1 to the least significant bit of the binary number and propagates any carries through the chain of half adder to produce the incremented value.